Hello, everyone. Welcome to our Satellite Embedding Deep Dive Workshop. It's great to see all of you here. This is a hands-on workshop designed to help you understand and explore the new satellite embedding dataset in Google Earth Engine. We'll spend some time learning about what this dataset is, what is it good for, and learn some applications. It is a kind of a really new way of looking at remote sensing and enables a lot of new use cases. So we'll kind of do a deep dive and understand different applications and see what you can use this for. This workshop will allow you to start working with the satellite embedding dataset for a variety of applications. We're going to cover some theory, understand, and wrap our head around what embeddings are, how to interpret them, and then once you kind of understand what these are and what they represent, then you'll be in a better position to apply them for your workflows. We have several hands-on examples. We'll start with some supervised classification workflows. We have a really nice example on crop type classification. This was something that was very, very hard. It's become much more accessible to a lot more people, can do much more easily using this new data set. Also apply this for surface water mapping. This data set is also really suited for supervised classification workflows, and we'll take a few examples and see some of the kind of differences on how you can use this data set versus using a source data like Sentinel-2 or Landsat. Finally, a part that I'm really excited about is the object detection, where now using remote sensing methods, you can detect objects in satellite imagery. And this is something that was very hard or almost impossible to do without access to high resolution imagery and deep learning models. But now with this data set, all of you can do this very easily. If you want to grab the presentation, you can click on this link, or you can scan the QR code, which will take you to this presentation, which has got all the information there. If you're watching this on a video, you'll find this link in the video description. Once you grab the presentation, you can come to the slide and get access to the course materials. The course materials are shared in form of a Google Earth Engine code repository. So if you click this link, you'll get a prompt to add a new repository in your code editor. And once you add it, you should see a new repository called users/ujjalgandhi/ge/satellite-embedding. And this has got all the code for the examples that we're going to cover, along with some supplementary materials. Just a note, if you add it and you do not see this repository, there is a refresh button in your scripts tab. If you click that, you should be able to grab that as well. Once you clicked that link and added the repository, you should see this new repository in your code editor. We have two folders. One is the hands-on folder, which has the step-by-step scripts that we have built, and a supplementary folder, which may get added with new scripts as we develop more applications. The structure of the repository is similar to how we do all our Earth Engine courses, where we have A, B, and C scripts. The A scripts are what we'll start each section with. We'll build the whole script together. I'm going to explain each step. And while I'm working on the A script, you can just look at my screen, try to understand it. Everything that I'm going to do is already there in the B script, which is the completed version of the A script. So you don't have to take any notes. You can just directly load the B script if you want the full version. But we'll kind of build the script from A to B step by step and understand that. And then finally, we have an exercise where you get to play around with the data set, try something new for your own region, and see how that works for the region of interest, for the time period of interest, and you can solve the simple problem using that. And that's how we're going to continue the structure. We'll start with some of the theory, we'll see some slides, and then we'll dive into the code. A bit of my background, I come from the traditional GIS and remote sensing background. I worked for a long time at Google. I worked on a variety of projects, including Google Maps and also Google Earth Engine. I was part of the Google Earth Engine team towards the end of my tenure at Google. I really liked teaching, so I finally left Google in 2020 and built Spatial Thoughts, where we create a lot of content and also teach live classes. Specifically to satellite embeddings, I've been working on this data set for 2 years now. We got early access to this data set, which was done a few years back. And then as Google kind of iterated and developed new versions, I was part of the team that tested this and kind of trying to figure out what are the use cases for remote sensing users. And finally, once they launched it to the public, we worked with the team to develop a set of tutorials, which I'll refer to later in the workshop, which are in the Earth Engine user guide. We can introduce yourself.
Yeah. So, hi, I have done master's in geoinformatics and worked with several government and private organizations. At Special Thoughts, I am a training associate. I provide assistance during the training and after the training, and also part of testing and developing some of the training materials.
Let's first understand what this dataset is about. We'll understand some of the basics, understand what you mean by embedding and how to think about it, and then we'll start playing with this in the code. This dataset was produced by a foundation model. Google called it the Alpha Earth Foundations model. A foundation model is a type of model which is a general purpose model. It's not designed for a specific purpose. So it's a deep learning model which says, I'll produce something which you can then use it for a variety of tasks. So it is not designed for specific tasks like classification or kind of crop mapping, right? It is a general purpose foundation model that is designed to make a lot of the downstream tasks easier and allow you to save some pre-processing of data. The different thing about this data set is many times when people have built those foundation models and they release it to the public, the models are released as deep learning models and say, hey, here's a model. You can take your own data, run this model, and it'll produce some output. But that requires you to have a lot of compute at your disposal. So if you want to run the deep learning model, you need access to a lot of GPUs. You have to download all the data, process it. Takes a long time to do this, a lot of compute, and that makes it very less accessible. So there are a lot of these models that have been developed by various companies and people. This was one of the first ones where they said, you don't need to run the model yourself. We will also run the model on all the dataset, the full archive of the dataset that were used there, and we'll give you the output of the data. We'll give you the output of the model as a dataset that you can directly use it. That means you can work with in a familiar environment. You can just have images, which are the output of the model, and you can just work with those images instead of doing the inference yourself. And you'll see why this is important, because to run this model, you need to have access to a whole variety of data set. The way the model works, it takes a whole bunch of inputs from all the Earth observation sensors, climate data, etc., and then it ingests all of this and produces something called an embedding, which is a representation of the pixel that is learned from all the data set for all the observations throughout the year. So each pixel embedding is a representation of that place on how that was represented in all this different data set in a whole year. And you get an embedding, which is at 10-meter resolution. So you get one pixel at 10-meter resolution. And in 64 bands, you get a 64-dimensional output, which is 64 numbers that uniquely represent that pixel at 10-meter resolution. And you get this new set of values every year. So that is an embedding vector for 2017, where you get 64 values for that pixel for 2017. You get another values for 2018, and so on. Right? And that's the output of the model. That is, you should be able to take this and then work on it for your applications. This was an animation that Google created to kind of visually understand how the model works. So let's take one place on Earth. So you take one place, any place you imagine. It has been observed by different sensors throughout the year. So you can see this one place. There are many, many images throughout the year. This is just one sensor. There are so many different sensors. All the sensors have imaged this place. Can we take all of this, put it into the model, and get 64-dimensional representation of this? So what the dataset produces is it takes the input stream of all the images that were collected from different sensors and says, I'll just give you 64 values that uniquely represent this place that has been captured by all of the sensors. So instead of you dealing with all those images, all those individual bands, you can then deal with only 64 bands of data. Embedding is kind of this new technology that allows you to compress a lot of this information into a small amount of information. And this is what enables this model to compress this very large stream of input data into just 64 numbers at each pixel. Each pixel is created from a variety of sources. The model has learned from all of the Sentinel-2 images for a year, all of the Sentinel-1 images for a year, all of the ScanSAR and Landsat-8 images for a year. So imagine you take all the images, and this is what the input that was given to the model for generating embeddings for 1 year. Along with the remote sensing data, you also get climate data, because a lot of applications require you to understand the response to different climate conditions. So Also, all the era 5 data for a year was also given to the model, saying, please learn how the pixel behaves in all of this climate variables as well. Plus other data sets like elevation data, gravity data, and a whole bunch of other information was given to the model. And the idea was that you learn from all of this data set for the entire year and produce a single 64-band vector. So you'll learn from all of this data set for the entire year and produce a 64-dimensional representation. So a single pixel will have 64 values, which is equivalent to all of this data set for a year. And all of you, if you work with any of this data set, you can imagine even a single image with 12 or 13 bands has so much information. Now imagine taking all of those images for a year, plus all of the different sensors, and then compressing down to small amount of information. And if done well, that means instead of using all of this data set for your task, you can say, I'll just use the embeddings as input. I don't have to use Sentinel-2. I don't have to use Sentinel-1. I don't have to use RFI. I can just use embeddings as my input, which has learned from all of this data for a year, and then I can use it for my task. So it saves you all the pre-processing that you need to do to work with all of these data sets. Why 64 dimension? Well, it's a choice you have to make. The embeddings architecture will say what is the representation you want? What's the dimensionality of your output? Some foundation models have chosen 250 bands. Some people have chosen 128 bands, etc. And again, the larger space you have, you can get more comprehensive input, but that means even imagine you have a 6-dimensional output. That means you have 256 bands. Working with those also becomes challenging for a downstream task. You'll have to kind of do some pre-processing. So again, Google made a choice to do a 64-dimensional, which are kind of a sweet spot between too few and too many. You give you a kind of right balance to say, I'll just treat this as my input instead of any of my other input data sources, and I'll still get the representation of the pixel from all the different input data sets. There's a preprint paper available on the model architecture that explains a little bit about how that was trained. The way the architecture worked was you have certain data sources which were given as input to the model and saying, hey, here is the input stream of Sentinel-2, Landsat, and Sentinel-1 data. So that's what was given as input. The input stream, which is they call video, which is each image is a frame in the video. So you can imagine a 1 year video of all the Landsat images, 1 year video of all the Sentinel-1 images. So that video stream was given to the model and say, learn how to compress this into just 64 values. And then from those 64 values, figure out how to reconstruct the same output. So I'll say, here's an image. Can you compress it to just 64 values? And then reconstruct the whole input video stream out of that. So the input was all of this. And the reconstruction part was say, can you reconstruct elevation data from this? Can you reconstruct gravity fields from it? Can you reconstruct climate data from it? So those were the target ones. So the model has figured out the weights which allows it to go from the Sentinel-2, Landsat, and Sentinel-1 data and reconstruct all of the target outputs. And that means it's learned how those are interrelated and it's learned how those patterns have affected the pixel. So that was the training architecture. So let's develop a mental model to understand what embeddings are, how to kind of think about them. For remote sensing people, the closest analogy would be PCA. Most of you would have done principal component analysis. This is a statistical technique that's been used in machine learning where you say, I'll give you a 12-band image and can you compute principal components? And it'll go and figure out 12 principal components. Typically, the first few will have all this uncorrelated information, and all the information that was contained in the 12 bands would be captured mostly in the first few principal components. And this is a statistical technique where you say, instead of using those 12 inputs bands, I can just compress it down to just 3 bands where I've captured most of the variance that was there in those images. This is similar to that. So mentally, you can think of these embeddings as kind of done a PCA on this large variety of input data, but it's not a statistical technique. It's a deep learning technique. The model has learned those patterns. It is much more multidimensional. Instead of just PCA that typically works with hundreds of inputs and compresses down to tens of inputs, this embeddings model has worked with hundreds of thousands of inputs and compress it down to 64 outputs. So again, mental model is like PCA. So think about how would you use PCA data in your task. You can apply this in a similar way, but again, they were created with a totally different model. Another way to think about this embeddings are that imagine a 64-dimensional space. This can be treated just as vectors. So imagine a 64-dimensional space. You have a vector of 64 dimensions, and each pixel with those 64 dimensions is a vector in that space. And each pixel would be somewhere on the sphere. The one property of the embeddings that were created by the Alpha Earth Foundations model is that they are unit length. That means you can think of, if you take the 64 values and compute the distance from 0, 0, 0 to the values, it will be 1. Right? So the length of the vector will be 1. That means the radius of the sphere in that 64 dimension would be 1. And that's a useful thing because a lot of the machine learning models also expect things to be normalized between -1 to +1. And again, this unit length has sort of really interesting properties that helps with the downstream task. So think about each of the embeddings and saying, I'll figure out where my pixel lies in this 64-dimensional space, and each of the pixels can be represented with just a vector. And then you can do all your vector algebra operation on this to find things that are close to each other, do vector math to figure out what lies on the other side, and so on. So you can think of them as vectors on an n-dimensional embedding space. The Satellite Embeddings dataset is given to you as images because they are generated in a continuous way. So for each pixel, there is a 64-dimensional embedding vector that was generated. For the neighboring pixel, another 64-dimensional vector was generated. So it can be easily represented as images. So say take a vector, put it as a value of a pixel in a 64-band image. So when you load these images, you'll see a 64-band image. And once you are in an image space, you can do all your image processing. So you can say, I can visualize 3 bands and see this in color. I can take the 64 bands, pretty much treat them as input features to my classification task and so on. So it has got these properties where you can see those embeddings because they are in this embedding space, which is pixel-based. But do resist the urge to interpret those embeddings. When you see this and people would say, oh, does the first embedding represent water? Or the first embedding is like, how green is that pixel? Not really. You cannot interpret this. These embeddings are learned from a large variety of input streams, and each axis of the 64-dimensional data can have some contribution from space, time, or values from different sensors. So you can't really interpret that. They're designed to be worked together. So for all your tasks, you should be using all of them together. Don't pick and choose. You might say, oh, in PC, I choose the first 3 ones. Can I just, instead of 64, can I just take the first 10? No. You will be missing out some information, which you do not know what that information is. So again, for all your tasks, you are expected to use all of them together. Some of the exciting stuff about this dataset and why it enables some of the new stuff is that a lot of our remote sensing dataset are just pixel observations. That means you have this pixel, it's been observed, it doesn't know what is going on around the pixel. There's no spatial context. And that means there are many tasks which you cannot do simply with this pixel-based methods. But when creating embeddings, a spatial context was added to each pixel. That means when it was learning what happened in this pixel, it is also looking at what happened around the pixel in a 1.28 kilometer window. And that means the 2 pixels, exactly the same values in all the sensors, but they're surrounded by different things, they'll have different embeddings. Very useful property that enables many interesting use cases. Each pixel also has the full temporal context. So the 64 values also represent how the pixel has been observed by all the sensors in a year. So imagine one satellite has imaged this pixel 30 times. All of those 30 observations are also included in those 64 values. And you saw there are so many different sensors that have gone into the model. So the full temporal context for all the sensors is also represented in all of those. And that means if you want to model crop phenology, instead of taking all the images and trying to model them yourself, you can now just take the 64 values. Representing embeddings as images also has this really interesting property. In Earth Engine, if you work with images, you know that you can work with images at different resolutions. And images, you can say, it's a 10-meter image, give me the version of this image at 20 meters. And Earth Engine has pre-computed pyramids where it'll take this 4 neighboring pixels, compute the average, and give you a 20-meter version of these images. And this allows you to do a lot of computations very fast. The same thing happens with embedding images. And the way they are designed is If you take 4 embeddings for 4 neighboring pixels, combine them into a single large 20-meter pixel, that 20-meter embedding also has the same properties. It's called the unit length 64-dimensional vector, which represent what happened in that 20-meter pixel throughout the year. So the same property kind of carry forward. And that also enables a lot of use cases where you can say, I want to detect something, but I want to do it at 100-meter resolution. You can just take the specified 100 meter as a scale of working, and you get the 100-meter version of those embeddings. So to work with this dataset, it's just an image collection in Earth Engine. You don't have to do any inference. Google has already run this model on all the input data, and it's available as an analysis-ready dataset for the entire year. Each of those 64 band images has the full context for the year. So if you load images for 2018, it has got the full temporal context for 2018. It has got spatial context of all the surrounding pixels. The images were pre-processed, so all the cloud mask, spectral transformation, everything was done. So you don't need to compute any indices or do cloud masking. You can just use those input data instead of using you can use the embeddings as input instead of using the source data. And these images, which encode the 64-dimensional embedding at each pixel, can then be used for your downstream task. You can use it in your classification or regression workflows. If you have a classification model, instead of you using Sentinel-1, Sentinel-2, doing data fusion, just use those 64 bands. And then just replace them as features, and the model will learn from that and it will give you predictions. Some of the more interesting use cases with this dataset are on clustering and unsupervised workflows, where you can group those pixels which have similar temporal and spatial trajectories, and then you can then assign different clusters on that, and that enables a kind of new interesting ways of working with classification. Chain detection, you can compare embeddings of 2 different years and see what has changed between those. So again, you can use them as inputs for your chain detection task as well. You can also find similar pixels. So you can say, I have this pixel, it is pixel containing some objects. I want to find another pixel which has the same objects. And the idea is if there's another pixel which has got the same object, it'll have similar embeddings. And you can then do a vector similarity search and find those pixels. So again, object detection is enabled by this similarity search. Very interesting and easy way of doing object detection instead of doing a deep learning model. Now let's start working with this data set. We'll do our first exercise where we'll learn how to load and visualize the embeddings data set. We'll dive into code editor now. We'll load the script 1A from our repository. As a reminder, the full script is already there in the B script. So right now you can just look at the screen, understand how to work with this data set, try to develop an understanding of this, and then we'll do an exercise when we come to the C script. Let's first look at the dataset in Earth Engine. So if you search for the satellite embedding dataset in the Earth Engine catalog, it's going to pull up the dataset page here. Here's the dataset listing in the Earth Engine data catalog. You can see the dataset is available from 2017 to 2024. Here is the description, just gives you a little more information about how to interpret this data. There is in the citation, this is the link to the paper. If you want to understand the model architecture, learn a little bit about how the model was trained, you can read this paper here. A nice thing about this dataset is Google decided to release this under a very liberal license. So that means if you want to use this dataset and build some commercial applications, do some derivative work, you are allowed to do all of that free of cost. There's no licensing required. You just need to attribute saying that whatever you did was using that. You can also export this, download this, and do something else entirely without Earth Engine. So kudos to Google for releasing this very liberal license. So you can do whatever you want with it. If you look at the bands tab, you can see the pixel size is 10 meters. We learned that this dataset was created from datasets of varying resolutions, but everything has been resampled to 10 meters. So the output embedding is at 10-meter resolution. And you have 64 bands here. And again, how to interpret them, what are the units? Well, this is just an output in the 64-dimensional space. This is just a number, there's no unit, there's no interpretation, there is no wavelength. So again, you can not interpret them by comparing it to a physical measurements. Okay, let's come back to code editor. We have our data set, we have the geometry here. So here is, I've drawn a polygon for a region where I want to kind of load and see the embeddings. So we have a polygon, we have a region, and we have the data set. And since it's an image collection, we can work with it very much like we work with any image collection in Earth Engine. So we say, I want to work with data for year 2024, and we apply a filter on the embeddings data set, and we get some images. Let me print this. Here, if I see this, you will see that there are 2 images that were found for this region. While the data set has inference at the global scale to enable ease of use, Google split each of these global images into tiles. Each of these tiles are about 150 kilometer by 150 kilometer. They are divided by UTM zones. So the source image will be in a UTM projection and in that particular size. So you can see each world divided into tiles. Each tile is in UTM projection, and you have 1 image for each tile. So in this region, we got 2 images, and they are kind of these 2 images that are given here. If I open up the properties, you will see the UTM zone. So you'll also know that what was UTM zone for the source projections. We want to just work and say, I just want to create a mosaic for this region. I don't really want to work with individual images. So we can create an image out of this multiple tiles using the mosaic function. So we're going to create this image. We're going to call this an embeddings image, and we'll call the dot mosaic function. So this dot mosaic will take all the images and stitch them together into a single image. A note is, when you create a mosaic, the output image does not have any projection, because this mosaic would have been created from images of different projections. So if I look at my output image, you can see if I print it, you will have 64 bands. The output images doesn't have a projection. It will be assigned a placeholder projection. Earth Engine calls it the default projection. So whenever you do a mosaic or a composite, you get an image, which is a placeholder projection, which is EPSG 4326 at 1 degree. Earth Engine says, I don't know what projection you want your output in. I'm going to keep that as a placeholder. Whenever you visualize it or export it, you will tell me in what projection and in what resolution you want it. I'm going to reproject all my source images to that projection and show the result. And again, this happens internally in Earth Engine. You don't have to really think about it. But again, if you ever are thinking, what if I want my output in a specific projection? Well, export the data in that specific projection, or in all the functions that you are doing analysis will give you a CRS parameter. So if you give a CRS parameter, all the inputs will be reprojected to that CRS, and all the analysis will be done on that. There's no global projection, which preserves all the accuracy. So again, if you say, what projection should I choose for my global data set? People have taken different approaches, like MODIS has a MODIS sinusoidal projection. Again, none of the global projection will have a good accuracy throughout the whole world. So instead, Google said, let's just stick with what Sentinel-2 does. We'll just use UTM zone for each tile. So you'll take images, everything is reprojected to UTM for that zone. The tile is then sent to the model and inferred, and then you save the results. And then you have those tiles in UTM projections. So if you download this, it'll be UTM, you can stitch them together by reprojecting. In Earth Engine, you can just do mosaic, and it'll get stitched automatically. We now have a 64-band image. You can see this is a 64-band image. Let's see what this looks like. Can we visualize embeddings? Now, human eyes, computers, we have restrictions. We can only visualize 3 things, because our eyes have 3 cones, computers have kind of 3 channels of information that we can present. We can't see all of the 64 band information at once. So one way to visualize is we can pick some of the bands that we want to visualize. It can be any 3 bands, and then we can visualize something. It'll be useful just to get a sense of what this embeddings look like. The values for the embeddings will be -1 to +1. So if I look at the pixel value, they'll have values from -1 to +1. So we can visualize this from a range of -0.3 to +0.3. And then we can pick any of those 3 axes. We can go from A00 to A63. So any of those 64 axes. Right now we're picking these 3 bands, and we can then add it to the map. So we are this mosaic images, the mosaic image that we've created, we're clipping to the geometry, and we're now visualizing it. And you see something on the map. This is a region around a reservoir in South India. You can see the reservoir is all, the center part of the reservoir is all in same color. That means they have the same values in those 3 axes of the embeddings. And that's why they appear in the same color. And everything that appears in the same color has the same values in those embeddings. But there's a lot more information. It's not just 3 bands, right? We have a lot more information. I can change it to any of the bands. So for example, I can say, give me 11, 26, 39. I can just take any 3 bands, and I'll see something different. right? I see some new information. This just helps you visualize what is the resolution of the data, how the landscape has been represented. If I zoom in further, you will see individual pixels. Each of this pixel is a 10-meter pixel that has the 64 values that has been learned from those input data sets. I can also inspect the pixel. If I inspect this pixel, you'll see that we have 64 values. So this is your embedding vector. So at this pixel, these are the values in -1 to +1, which represent this pixel in this digital space. So everything that this pixel has been observed by the sensors, everything has been compressed into the 64 numbers. If I compare it with the neighboring pixel, they'll have slightly different values because, again, there is a different temporal context, different spatial context, different observations, and the embeddings will differ. You can see there's a lot of precision to this. Again, resist the urge to truncate this because the precision also captures a lot of information. So again, use the values as it is with the full precision, and then you'll be able to replace your input data stream with this 64 numbers here. And the idea would be you can treat this as a vector or in a 64-dimensional space. If there's another vector which is close to it, that means it is representing the same thing. If there is 2 pixels which are growing a crop and they're growing at the kind of same pace, they're growing, this is the same crop, everything is the same, they'll have very similar embeddings. But if there are 2 crops which are different phenology, they have different crops, they'll have different embeddings. So by kind of comparing the embeddings, you can find out if the things are similar or dissimilar. Now, this visualizing 3 bands at a time is kind of painful. If you want to really understand and kind of visualize what the embeddings have learned, a much better approach will be to visualize them using unsupervised clustering. So we'll take all this information, we'll train a clustering model to say, show me the groups of pixels which are similar. So we'll do an unsupervised clustering approach to visualizing this data, which allows us to now say, I can't visualize all this information, but I can group them into similar things, and I can see what are the different things which are similar into this particular region. In Earth Engine, we have many different clustering algorithms. There is a k-mean algorithm. So this is the k-means algorithm where you say, I'll train a model that will give me some input data. I'll group them into groups of number of groups which is specified, where each group will have values which are similar to each other. The way you train the model is you sample your image. So here we're going to take some random samples. We'll take our image, sample about 1,000 pixels here. So we'll say in this region, give me 1,000 randomly selected pixel values. And that become our training data for the clustering algorithm. Here you can see this is what the extracted feature looks like. At 1,000 random points, we just got those 64 values. So now we have this 1,000 values, which we can now go and say, please train a clustering model where you group the embeddings which look similar into the same cluster, and then go and predict in the images, if you see a new pixel which you've not seen before, assign it to one of those clusters that you found. Here is a simple function that written to train a model. So here we are training a cluster model with the number of clusters. So we say, give me a model which can group this whole image into 3 clusters. And if I do this, it'll train a model that'll say, given all this training data, all this 1,000 samples, I'll figure out where are those 3 clusters in the 64-dimensional space. I'll group those things together. And then for each pixel, I'll assign to one of those clusters, which is closest to that particular vector. Let's visualize this. So I'm going to say, give me an image clustered with 3 clusters. So I'll take this embeddings image, extract this 1,000 pixels with 64 dimensions, do a clustering and get a clustered image. This image will now have only 3 values, 1 to 3, cluster 0, cluster 1, cluster 3. So each pixel is assigned to one of those 3 clusters. And now we can visualize this much better. There is a nice function. If I want to visualize this, I can say I want to add this, but then I want to assign some color to each of those clusters. There's this nice function called random visualizer. We'll say it will assign some random color to each of the unique values in the image. And now I can clip this and visualize this. So I'll visualize this and we'll just say this one is a 3 cluster visualization. And now what we're going to look at is what the embedding is learned about this landscape in the whole 64 dimensions. but grouped into 3 groups. So if you look at this region and say, just divide this into 3 different groups, you will not know what group is what, but this is what the embedding said. This pink pixels are all similar things. The yellow pixels are all similar things, and the green pixels are all similar things. If you compare it with the base map, you'll see that the pink ones are obviously water. The yellow one is kind of temporary water, where there is kind of some vegetation. It's got flooded vegetation around this. And the green one is everything else. Right? So now this is a great way to visualize what the data set has learned. What do the embeddings represent? One thing you'll notice, if you've ever done clustering, you will never get this clean boundaries. Right? You see very clean boundaries. There's no noise, no salt, pepper noise, because of the spatial context. The embeddings also look at the surrounding pixels. That means if there is this salt, pepper noise, that gets removed. So again, you don't need to do post-processing as well. Many of the remote sensing tasks where you do some workflow classifications, you have to post-process. Here, you don't post-process because, again, you get very clean cluster boundaries. We can keep going and say, oh, but I want to actually visualize 5 clusters. So let's see how this landscape looks like with 5 clusters. So I'm going to just do changes to 5 and run this. So now the same landscape will be split into 5 groups of similar things. And now you will start seeing more details. You can see the water and this kind of vegetation around it stays the same, but then now you're seeing agriculture and urban being split into different things. There is also different kind of forest and agriculture being split into different things. So now again, this is all the stuff that is close together in this embedding space. You can keep going. You can kind of do as many as possible. The embeddings have learned so much of pattern, you can kind of keep going and splitting into even more number of clusters. So let's do 10 clusters and see if I want to divide this landscape into 10 groups of similar things, what they are. And this will give you kind of a much better understanding of what is represented in the embeddings for your region of interest. And this will be a first step before you start using it. I highly recommend doing this and say, can I just do some clustering and figure out how do these pixels are grouped? It has learned the phenology, it has learned different things, but it may not have learned the things that you wanted to. So you'll have to kind of say, can I split this into different groups and see I can separate out things I want to separate. And so this is a good way to explore this data set and understand how it has learned the landscape. Yes, I have to replace the code. We have the 10 clusters. Let's do an exercise where you can play around with this and figure out how your landscape looks in different embeddings as well as with different clustering outputs. Right now, we can explain the exercise.
So in the exercise, you are just going to explore the data set and visualize a region of your interest, a region that you are familiar with. So here you can just delete this geometry and create a new geometry at your choice of location. Just see your hometown or something and draw a geometry here. And run this and you will see the composite here, and you will just have to play with the bands. You can visualize different bands, and also you can see how many clusters you can create and what all features it is identifying. So try this, just draw the geometry and then visualize different clusters and use different bands.
Right, well, let's try the exercise 1C. It'll be nice if you can play around with your region to get an intuition around how embeddings behave and see if you can derive some useful understanding from this exercise. Let's learn how we can use the satellite embedding dataset for unsupervised classification. In kind of remote sensing, unsupervised classification is not very widely used because it requires a lot of pre-processing, and also the results you get, they still have to be labeled. So most people say, if I still need to collect field labels, why even bother with unsupervised approach? But with the satellite embeddings, they're actually quite useful. Many applications that you can use it for, where you don't have field data and you can still derive some useful information out of this. And we learned that embeddings can be thought of as this vectors in this 64-dimensional space. If the vectors have similar values, they are close together in the space, and the clustering algorithms are really good at grouping them into the same cluster. So you can see if the embeddings appear together in the 64-dimensional space, the algorithm will just say, all of this are representing the same thing, I can group them together. And with the spatial context and temporal context, you get really nice, clean cluster boundaries out of these algorithms. And then we can apply some techniques to label them automatically as well. Again, the level of clustering that you want will depend on the application. You can say, I just want 2 clusters. And the algorithm say, I'll divide this space into 2 clusters where I'll assign each pixel to the closest cluster to it. And you'll get 2 groupings, which are kind of interesting. And you can say, how, if I had to divide this landscape into 2 different things, how would I do that? You can keep going and say, give me 5 different clusters. And what those are, you can interpret those. You can keep going and say, I want more and more details. The clustering algorithms will make tighter and tighter clusters. And you'll get kind of information that is much more nuanced that can be compared. Once you have those clusters, there are different techniques that will cover. You can apply local knowledge. You can say, I know this area very well. I know that this cluster is actually this type of farming. Or you can say, I have some rules where I'll compute some index value for each of those clusters. And the one having the high values in this index is actually surface water. Or we'll apply this technique for doing crop type mapping. Crop type mapping is one of the harder problems in remote sensing, very inaccessible to most people, requires lots of data pre-processing. You need to model the entire phenology because you want to now classify different crops. You need to know how they grow and what is the growth pattern. And that means you need to now take data for a long time period, model that, you do some harmonic modeling, then computational intensive, requires a lot of specialized tools and knowledge to do this. For certain kind of crops, again, just by looking at each pixel is not enough. You need to know what is the pattern, because some crops have a unique pattern and you need that pattern of farming to separate them. So again, you need to add the spatial context. You need to do sensor fusion. For crops, you need to also look at the structure of the farm. The height of the stalk and height of the plant is also important for doing crop classification. So again, people typically take optical and radar data, do some sensor fusion and use it. Again, lots of pre-processing, challenging to do and challenging to do it right. You also need to measure the response to climate variables. You want to separate out crops that have different responses to rainfall. All of this has to be modeled, and that means you need to incorporate climate data. So again, all this is very, very hard. People typically do a few of those and kind of get decent result. But again, doing all of this is very, very hard. Plus, even if you did all of that, it's still not complete. You need high quality labels. That means you need to know in a region, I need to have labels for each of the crops that is growing. So I need to say there are 5 crops. I need to go and obtain field samples for each of those crops. And I can't go at random times. I need to go in a specific time which matches my images. So I need to get yearly labels or kind of go in a specific season, collect labels. Very, very labor intensive, not feasible for many tasks. So again, this becomes quite challenging. But with embeddings approaches and unsupervised approach, you can actually address many of these challenges very effectively. Embeddings already include temporal context for the entire year. So you don't need to do any time series modeling, no harmonic modeling. It also has the spatial context, so you can detect things like plantations, etc. easily. You don't have to model for spatial context. Includes both optical and radar data. So again, you don't need to do sensor fusion. The data itself has the learned from both optical and radar data. Includes error 5-line variables. So again, you don't need to measure, you don't need to model the response to climate variables because it's already been modeled as part of the learning process. So now we can use embeddings directly for our crop classification task. We'll first go and start building code that takes the embeddings, do an unsupervised classification. We'll identify clusters of different crops, and then we'll come back to the presentation and learn how to label those. So let's go back to the code. We're going to work on script 2 here. Here we're going to take a problem of crop classification. This is a real example, which will show you the power of this approach. This approach is an unsupervised approach to crop type mapping, which requires knowledge of the region and some aggregate statistics, which both are easily available compared to the obtaining field labels. So this approach will work if you know a region. You can say, I know a region, I know what kind of crops grow there. I know roughly what is the kind of crop calendar, what are the different cropping patterns in this region, and I can obtain some high-level data on what is the distribution of crops. If you have all of those, you can do accurate crop mapping, and we'll demonstrate this using this example. Here we are working in Iowa, this in the US. This is the Corn Belt in the US. There's a lot of agriculture here. This is county called Sarasota County in Iowa. There are two primary crops. If you look at the images, there are multiple crops here. And this has only two primary crops, corn and soybean. And I want to map all the soybean and crop. I don't have any field data. Can we go and map that? Also, in the US, you have larger farm sizes, clean farm boundaries. All of this makes it easy. In other parts of the world, it becomes a little challenging. But again, you'll see that embeddings actually provide you a much easier starting path to crop mapping than other approaches. So we first take the region. So here we are taking the county's data and filtering it to the specific county boundary. We have a geometry. We take the embeddings data for a specific year. Here we are looking at 2022, and we create a mosaic. And this is what the embeddings image look like. Again, we take any three bands and visualize this just to kind of see what embeddings are overlaid on this region, what it look like. You can see there are different colors. Each of the colors represent a different crop because there's all crops have different phenology, different pattern, and they end up with different embeddings. You also see there is some other region, there's urban areas, roads, they appear in different colors because they have different embeddings. So the first things we want to do is for crop type mapping, we want to apply a crop mask. We want to remove all pixels which are not agriculture. So we'll have to obtain a data set which has classified this region into crop versus non-crop. There are many good global data sets. There are many regional data sets. In the exercise, we have an example of ESA World Cover, which is a decent global level data set you can use to obtain a crop mask. This is US, so there is a nice crop mask available from CDL. So we'll just use the crop mask from CDL and remove all the pixels which are non-crops. So here we are using the CDL data, which is the cropland data layer from USDA. And here we have a crop mask where we have ones and zeros. So you can see in this image, everything that is green, which is pixel value 1, which is an agriculture pixel, and white is non-agriculture. So if I look at with the base map, you can see everything that is non-agriculture will be masked out. So we need to obtain a crop mask where you have ones and zeros. 1 is where there's an agriculture, 0 is where there's no agriculture. And now we'll go and apply this and say we'll mask out our embeddings image with all the non-cropland pixels masked. And this becomes our input to the crop classification. So we just take the image where we have removed all pixels which are non-cropland. So now all the urban stuff, all the roads, all other kind of forests, etc., has been masked out from the image. And all that remains are agriculture pixels. And now our task becomes, can we divide this into different crops? Can we classify all of the remaining pixels into a specific crop pixel that we can map? This is where your local knowledge will come in handy. Now you pick a region, a district, a county, and you say, based on your knowledge, how many crops are there in this region? And that will allow you to build a clustering model to say, should I divide this into 3 clusters, 4 clusters, 10 clusters? And then I can obtain clusters representing each of the crops. Let's do our clustering. We'll extract training samples. So we have our embeddings image. Let's say I want to extract 100 samples from it. And I'll overlay my data on top of this. So I say sample 100 random points from this particular image and extract those 64 values, which I can train my clustering model. You'll see that when I asked for 100 samples, I got 99 samples. The reason is many of my samples will fall into the masked areas. So you can see there is my sample was inside of this masked region, so that I got null values. So this will often happen that I want some 1,000 samples, you only get 500 because some of the pixels will fall into this masked region. One of the nice workaround for this is to say, don't use this sample method, which is just randomly sampling pixels from your entire region. You can instead use the stratified sample method, which allows you to say, take another band of information where you say, I have my clustering image, which is masked. There are a bunch of pixels which are masked. I'll add the mask as another band. So I have a 2-band image. And the stratified sample will say, now collect n number of samples, collect 1,000 samples for each of the values in this band. So it'll say, give me 1,000 points where this value is 1, give me 1,000 values, 1,000 pixels where the value is 0. So I get 1,000 in each of those classes that are included in this band. And since we say drop nulls is true, the stuff that is null values, which are where the mask was 0, they'll all be null values, they'll get dropped out. And now when we do this, we'll get exactly 1,000 pixels. And this is kind of the way to extract exactly n number of samples from a masked image in Earth Engine. So now if I look at my training samples, they'll all be 1,000 images, 1,000 samples, which are exactly that. Right? So, and they all will fall on a non-masked pixel. Once I have my samples, I can now train a clustering model. One note is here we are working in a pretty large region and we have 1,000 samples. Sometimes when you're trying to visualize this or even trying to build a model, your Earth Engine will say computation timed out. Extracting this pixel values, sampling images is a very computationally intensive process. So if you are working in even larger region, you say, I want to do this for a large state or a very large region, and you want to extract, let's say 100,000 samples. That process will not finish in 5 minutes, which is the time limit for the code editor. So if you're trying to interactively visualize the results and you say computation timed out, you can export this data. A good practice is always to just say, I'll extract my samples, I'll export them as assets. The export can run for as long as it needs to. And once I have them as asset, I can then import it and continue my classification task. In our full example, we have the code for export and import of the samples from here. For now, for this region, this example works interactively, so I'm not going to bother exporting this. Once we have the training samples, we can do our clustering. For this region, we have only 2 major crops. So here we have mainly corn and soybean. There are a bunch of other smaller crops, and then maybe there are some other crops as well. So we can say, instead of having a fixed number of clusters, there is this really nice cascade k-means algorithm, which takes min and max clusters, where you can say, give me anywhere between 4 to 10 clusters. You can also change it. And you'll figure out, based on the training samples, you'll figure out what's the optimal number of clusters for it to split this data into different groups. So you don't need to know the exact number of clusters your region has. You can give a range of clusters. Here we say, I have 2 major crops, so there are definitely 2 clusters. There's also a bunch of other crops in the region. So again, I have 3 to 4 clusters. So 4 is a good number to start with. You can go to a higher number if you want to even separate out the other crops into different groups. This approach works well where you have at least a few primary crops in a region. If you say, I have a whole bunch of, like I have 30 crops, which are all kind of all scattered all over, 30 clusters won't perform as well. But if you say, in this region, there are 5 major crops or 4 major crops, you can kind of separate them into their individual clusters, and then you can label them easily. So we do our clustering on that masked image. So masking is important because we don't want to worry about clustering urban areas or water bodies, etc. So we only cluster the agriculture pixels. And you can see I get pretty nice clusters out of here. You can see there are 2 major clusters. You can see this one is a green and pink cluster. They are different crops. If I compare them with our base map, you can see they are all different farms. They're growing different things. And I'm able to kind of separate them out easily. I still don't know which is what. I don't know what is pink. Is it corn? Is it soybean? We don't know. But we have at least identified different crops. There are some regions surrounding it. Edge, there is some spatial context because of the road and urban region. So they are kind of grouped into a separate cluster. But otherwise, we get this kind of 2 clean clusters that have kind of captured the 2 major crops in this region. Now, the challenge is, how do we label that? Let's learn some of the labeling techniques. How do you label crops? Well, if you have field labels, when a small number of samples will do. So let's say your crop of interest is corn. And you say, I have this 10 samples of corn for this county and for that year. And you can just overlay it on top of the map. And you can see which cluster does it overlay with. One major problem with crop classification is if you want to do a supervised classification, you need all the counter examples. If you just want to classify corn, you still need to know which pixels are not corn. And that means you can't just randomly assign other pixels. You need to kind of go and pick up non-corn pixels. In this approach, you only need labels for one of the classes of interest. And you can say, I overlay this. Maybe my cluster was split into 2 clusters. All my points are overlaying with just two of these clusters, and now I've found all the corn pixels in my region. Right? So with sparse data or labels of a single crop, you can identify all pixels of the crops. A more scalable approach is to use aggregate statistics. This is an approach I first learned a few years back. I've linked to the paper in the last slide and on the course materials, where they use a really smart technique of taking the published statistics at the district level or county level. Most countries in the world, they publish statistics of crop production, cropped areas for each of the admin units. So you'll find publication from government saying that this county or this district in this year produced this much, had this many acres of corn planted. We don't know where is that corn pixels, but we know in aggregate in this district, this was the total area. It doesn't even have to be very accurate. You just need to know an approximation of the cropped area for that region. So we can say in this particular county, we found some publications which says in this year, in this county, there was X amount of acres of corn, Y amount of acres of soybean. Now we go and compute the area of different clusters. So we say cluster A, what is the area? Cluster B, what is the area? Cluster C, what is the area? And then we just sort them by area and match the areas. So the highest cropped cluster will be the highest crop statistics. So say in my crop statistics, in this region, the highest area for the crop was corn, and that means that the cluster with the highest area in my map is corn. And this means if you have just aggregate statistics for region, you can now map all the crops in that region. Okay, let's see how this works. So back to our script here, we have the clusters. We don't know yet what clusters are what, so we want to now label them. We first calculate areas. So I'm going to copy paste some code where I'm going to compute the area of each cluster. We are using a grouped reducer to compute areas. We are also dividing this into acres because the crop statistics we are getting are also in acres. So we get in Earth Engine, all the areas are square meters. We convert it to acres. We get for each of the clusters. So there are 4 clusters in this image. For each clusters, we'll get the total areas. We do some post-processing, and now we have our results where it say cluster 0 has this many acres of area. Cluster 1 is this much area. Cluster 2 is this area, cluster 3 is this area. I still don't know what cluster is what, but I know the area of each of the crops in the region. We know that there are 2 major crops, so we just say, I'll just pick the top 2 clusters. So we just sort these areas by this results by area, pick the first 2 ones, so there are the top 2 clusters by area. So this is a cluster number 1 and cluster number 0. These are the 2 main clusters. There's 131,000 acres and 103,000 acres. Still don't know which is which. So we now go and look up some crop statistics. In the US, there is a USDA NASS website which publishes annual statistics. You can go and download this. I've put the link. This is the link for year 2020 from 2023. This is the cropped area for 2022. And you can see these are the cropped areas for each of the crops. It says corn was this much acres and soybean was this much acres. And now I know that the highest cluster with the highest cropped area is corn. So cluster 1 is corn, cluster 0 is soybean. They don't match exactly, that's okay, because again, they are done by different approaches, but we have now labeled our clusters by comparing the areas. There are many countries who publish this. In India, there's a website which has got, I think, last 10, 15 years of crop statistics that are published at district level. Many other countries have that. They are much more easily accessible than field level labels that you need for supervised classification. So now we label our clusters from the crop statistics, and then we can create our crop map finally. So we do this automatically, where if you have some CSVs, you can just pick those automatically for each year and say, get me the cluster for the highest area, cluster for the second highest area, take this, and now we have our crop map. To visualize this better, I'm going to also add a legend to this so we can kind of see this in more details. So here is our final classified map. We started with just satellite embeddings. We did a crop mask. Whatever agriculture area was remaining, we grouped them into different clusters, picked the top two clusters, which are the two main crops in the region, and then compared their areas with the published crop areas, and then sorted them and assigned the values to each cluster. And now we have identified which farms are corn and which farms are growing soybean for that year. And then we have another cluster, which is the other ones. Now you might say, how good is this map? With no data, with just satellite embeddings, we were able to do this. To compare this, in the US, at least we have a really nice data set. USDA publishes the annual crop maps, which they have done with a lot of field labels, massive exercise, and now we have this data. So if I compare this data from CDL, you will see that I've loaded the map from CDL, which has also corn, soybean, and other crops. First thing you'll notice is, again, there's a lot more noise in this data in the CDL, because again, it's a pixel-based classification. It's not doing object-based classification. There's a lot more noise in this versus if you compare this with other crop map that we've detected, much cleaner boundaries. You don't have to do post-processing, get much cleaner boundaries. And if you compare them between each other, you'll see that we have a pretty close match to an officially published crop map for this region. This is a demonstration of an unsupervised approach that, combined with your local knowledge of how many crops are there in the region and official aggregate statistics, you can produce an accurate map of crop types in the region. There's a question on double cropped areas. So the way you will see double cropped here is, if there is a farm, single cropped and double cropped, they'll have different embeddings. They'll be put into different clusters. You need a way to then separate them and label those clusters. Right? If there is, for example, if there is rice and wheat in one farm and only rice in one farm, they'll have different embeddings. They'll be put into different clusters. You may then choose to label both of them as rice or separate them and say this is rice and this is rice plus wheat. All right, let's do an exercise where you actually get to try this out for your region and see how well this approach will work for your region of interest. So let's do the exercise 2C.
So for the exercise here, similarly, like what we saw, we have the embedding data set and we are using ESA world cover for creating the crop mask, and we have the crop mask, and then we have embedding image or the masked region, and then we are having clusters. So this is the image for Bargarh district of Odisha, which has primary crop being rice, and we are using clusters for maybe say 2 to 5 clusters. Your task is to create another geometry, so you can just don't use it and go to region of interest where you know the types of crops present in the region and you know how many clusters that you should be creating in the region. So just go to that region. You can again same way use the geometry tool and create a geometry, and here, if you'll run this, you will get the embedding image and crop mask. You can just decide the number of clusters based on the knowledge of the region. If you have only 2 types of crops over there, set the number of clusters accordingly. If you know that there are more clusters possible in the region, just change the type of number of clusters, minimum and maximum. So here, once you click on the pixel, you will see the NDVI trend over there. And this is the chart that is being created for NDVI. So you can try this for your region, set the number of clusters and see how NDVI looks for different pixels.
So in this region, for example, when Vigna chose this region, we applied a crop mask with the clustering and we get some clusters. So here we got 2 clusters because the minimum cluster was set to 2. If you know there are more crops, set it to a higher number. Now this has been separated into 2 clusters. We don't know which is what. Based on your knowledge, you say, I don't know what is what. Maybe this is a single crop, this is a dual crop. If you want to understand more about the pixel, click on a pixel from one of the clusters, you'll see the NDVI time series. And that'll help you interpret this better. You said, oh, I know this pixel must be rice because it's planted later in the year in this region. Or maybe this is a dual crop farm. That's why it's been separated into a different cluster because I see 2 peaks in my NDVI. Right, so this will allow you to interpret your clusters a bit better, and based on your local knowledge, you can then think about what those crops might be here. So let's try the exercise 2C, where you get to try this unsupervised crop type mapping approach for your region of interest. So we learned about an unsupervised approach to crop classification. You can apply this unsupervised approach to other line cover types as well. A common way to do this on surface water, where you can say, I want to detect surface water I can use this unsupervised approach. We'll do the clustering. So once we did the clusters, how do I identify which cluster is water? You can do some analytical approach where you can say, I'll take a Sentinel-2 image of the same region, compute NDWI, where NDWI is an indicator of surface water. Where there is water pixels, NDWI is very high. So you'll go and say, I'll calculate NDWI for each cluster. I have 10 clusters. I don't know which is water, but I know that water will have high NDWI. So I'll calculate NDWI for all clusters, and then I'll sort all the clusters based on NDWI. And I'll pick the cluster with the highest NDWI, which I will tag that as water. So now, even without any labels, just using a pure unsupervised approach and based on some analytical inputs of NDWI, I'm able to tag cluster, which is surface water. This algorithm is called water detect. It was described in a paper a few years back. We have implemented this for Satellite Embeddings. It's there in your supplement folder. If you want to try this out for your region, you can use this where you just take embeddings, cluster it, and then pick the cluster with the highest NDWI and has water. And again, you can see from the screenshot here, you get really clean boundaries of surface water. You also get detections of very, very small water bodies. So again, something that not other datasets can replicate very easily. Here also, you'll see that there is always some confusion. Water looks very similar to like building shadows or dark. Built areas have very similar values. So some of them might see the confusion. But again, this is an example of an approach where you can still get to a fully automated classification based on unsupervised approaches. Let's move on to the supervised classification approach. In supervised approaches, you have label data and you want to then classify your image into different classes. Traditionally, you would use your satellite bands as input features to your supervised classification task. If you have embeddings, embeddings have captured a lot more information than just the spectral bands of a single sensor. So instead of doing all the data fusion and doing all the modeling, you can just say, I don't want to figure out what index to compute, what bands to add. I'll just replace my whole input feature space with just embeddings. So instead of using and modeling my feature space, I'll just take those 64 band embeddings and use them as features for my classification workflows. Embeddings work really well for low shot classification. That means just with few samples, they can separate out different classes. In a typical classification workflow, you need hundreds of samples to do it accurately. If you use embeddings, just with a handful of samples, maybe 10, 20 samples of each class, you can actually get a pretty good result because the embeddings can be separated much more easily by the classifiers. If you understand how if you understand how embeddings work, they are kind of described as vectors in n-dimensional space, and you want to kind of separate them into groups of embeddings which are close together in space because they'll be representing the same object or the same class of line cover. There is a classifier called KNN, which is like unsupervised approach to supervised classification, where it says, give me a label, I'll group the input space into different clusters, and then use your labels to assign the labels to the cluster. So if you're using embeddings as input to your classifier, other than using random forest or some other tree-based classifier, a KNN classifier actually performs much better. So if you have an existing classification, you want to try embeddings, you'll replace your input features with embeddings, change your classifier from random forest to a KNN classifier, and you should see a huge jump in accuracy. And the reason it works well is because they are inherently suited for kind of partitioning the embedding space. Versus random forest is more non-linear approach to separating those feature space, and they do not work as well as KNN for separating. But if you want to do regressions, so you have your input data and you want to predict numeric value instead of a class, random forest works really well for regression classes as well. So if you have doing any regression, you're predicting any numeric value like crop yields or water quality or other things, you can just replace your input data stream with just embeddings and use a random forest classifier in a regression mode for doing this. In all our testing and working with classification, what we found is if you have a lot more samples, if there's a lot of variance in your samples that you added, the classifier doesn't perform as well. So it's counterintuitive. The less number of good samples you have, the classifier actually performs much better, especially the KNN classifier. So if you say I can generate 1,000 samples, but some of them might be mixed, that is not as good than just doing 10 samples. So just have fewer high quality samples, which work much better with embeddings. The recommended approach is you just start with a small number of samples. In many approaches, just start with 5 samples for each class. Generate the output, see how it looks, and say, oh, it got confused here. Maybe this thing was actually class B, but it got classified into class C. Just add a class B sample there, rerun it. And once you do it a few more times like this, where you correct with counter examples, where the classifier made a mistake, you can iteratively fix and improve your classification. And this, with just a few examples and counter examples, the classifier usually does much better job. Now, why should you use embeddings? One is it's very easy. Instead of doing all the data processing, just replace your features with embeddings. But also, you can now do something which was not possible before. So if you need spatial context, let's say you have a pixel which is bare pixel, but one is on a dirt road, which is a linear feature, versus one is on an open land. Regular classifiers cannot separate them differently. They'll be both classified as the same thing. But since we have spatial context, a dirt road can be classified differently. If you just have an example and a counter example saying this is dirt road, this is bare land, the classifier will learn that and separate them out. So again, because spatial context really helps here. If you have a vegetation that has different pattern, like forest plantation is very hard to classify because it just looks like forest, but it's a kind of different pattern. And again, because you can have spatial context, you can actually have a class which can be classified just with a simple classifier with embeddings as input space. If you want to classify things that change during the year, again, you don't need to model any of the time series, you just add those input features and they can be separated out. And again, many of the kind of things which were not possible before can be now classified much more easily with the traditional classification workflows. We'll do an exercise to map mangroves. We'll learn the classification workflow. If you've done classification in Earth Engine before, this will be very straightforward. If you've not done classification in Earth Engine before, this will show you kind of the step-by-step. As we're doing this, I'll explain some of the nuances and some of the differences between using your traditional satellite images as input versus using embeddings as input to your classification task. We're going to do a simple 3-class classification, mangroves versus non-mangroves. We'll do mangroves, water, and other. So we'll try to pick a region, pick a few points on mangroves, few points on surface water, and all the other things will be clubbed into other. One thing to note is embeddings are really good at this kind of binary or a few class classification. In your traditional classification, if you group everything else as other, it'll be very hard for the classifier to kind of be effective because there are so many other things. There's urban and agriculture and forest and all of that. Embeddings do a good job even for binary classification. If you just did mangrove versus non-mangrove, it can actually do much better. So again, binary classifications, small number of classes where one class is all other land cover classes versus other classes, they all tend to work quite well. Let's move to our code. We have the script 3A. Here's a region where there are some mangroves. We start by a Sentinel-2 composite. We use the Sentinel-2 composite because we need to pick training samples. So again, you can't visually see embeddings easily because there's so much information. So we just use our natural color or false color Sentinel-2 composite to interpret this image. Here in this image, you can see there is a mangrove forest here. You can kind of compare the high resolution imagery along with your Sentinel-2 image to say, here is some mangrove forest, here is some surface water, and then there are other classes. And I want to classify this scene into these 3 classes. We will first need to collect some training samples. So we'll go and create those training samples. I'm going to use the Earth Engine code editor to collect those samples. I'm going to add a new layer, and we're going to go to the settings. Here, I'm going to make this as a mangrove layer. This is a feature collection where I'll hold all the mangrove points. We'll turn it into a feature collection. We need to assign a property to hold our class. We'll use land cover as a property name, and we'll say this will be class 1. And now we have this mangroves layer, and I'm going to drop some points on the mangroves here. So I'd say this is a mangrove, this is a mangrove, this is a mangrove. That's it. Okay, so I have this few samples of where there's mangroves. I'm going to add a new layer. We'll say this one is water. And turn it into a feature collection. Just say land cover 2. And I'm going to select this layer, drop some points on surface water. And I'm going to add another layer, and this will be other. So all other classes would come here, and we'll just add a land cover property is 3. And let's just drop some points on other kind of land cover. And again, we just have 3 points. That should be enough to get us started. And again, the way you would build this is whenever the classifier makes a mistake, you go and add a counterexample. And the classification will then learn how to separate those. And again, it says there are so many other things. So it might say, oh, this particular piece is closer to mangroves than this urban area. So I'll classify this as mangrove. But then you say, no, this is not a mangrove. This is actually agriculture. So you'll go and drop another point here and you fix your classification. So we'll take our embeddings data. So we take our embeddings image, we filter it for the year that we are classifying, and we'll create a mosaic for this. And we'll take our training samples. So we'll say we have our training samples. We'll merge all of our input feature collections. We'll say mangroves.merge, water.merge, other. So this will be our training samples. If I print this GCPs, this is just a set of 9 points that we have collected, which is only called this land cover property. We're going to go and sample this embeddings image to get our training features. In a regular classification, when you sample this, you are using Sentinel-2 image or some other composite image that you created, that you are extracting the pixel values to train a classifier. Here, we don't do any of that. We just use the Sentinel-2 images to collect some training samples. But when we are training the model, we are using the embeddings image. So our training features only have embeddings. And again, we don't pick and choose what bands of the embeddings layer. We just use all 64 bands. So now when we have our features, this is what our features are. So our k-ren classifier will say, given this embedding vector, I need to assign a label 1 to this. And then once it learns this pattern, it says, I have a new embedding vector. It'll find the closest class that this model is predicted. So it says, oh, I have this embedding vector is closest in this embedding space to a land cover class mangrove. And I'll assign the class mangrove to that. So we'll now train classifier. There are classifiers here under the e.classifier module. You can see there are classifier. Most recommendation for Earth observation data classification is usually random forest, works really well. There's also gradient tree boost, which is a newer classifier, which also works well. These are both tree-based classifiers. Both work great for regressions with embeddings. But if you want to do classification with embeddings, the KNN is the better classifier. So we'll use the KNN, which just says, I'll train a nearest neighbor classifier. So let's do a classifier. We'll do EE classifier. KNN, and we'll just train it with our training features. So we have the training features, which is the vectors that we sampled from the embeddings image. The class property, we have labeled this with land cover. So it says learn from the property. So the class property you want to predict is in the land cover. So whenever you build a model, you should predict that as 1. The input properties are all the bands from A00 to A64. They are the same as the embeddings image band. So we just say use the band names from the embeddings image and it's your feature space. And we have trained our classifier, and now we can just go and classify the image. So at this point, the model will train the classifier and classify the image. Before we visualize this, note if you want to scale this to a larger region, we recommend you export this classified image before visualizing it. If you're trying to classify a whole coastline of a country and detect mangroves, this is going to time out. It's a kind of large operation to do prediction on so many pixels. So if you want to avoid the timeout, export this classified image, let it run. Once the image is exported, import this asset, and then visualize that. Since it's a small region, we can skip the export part and just visualize it directly here. Yeah, I believe I have a typo. So here there was a typo, so I'm going to fix that. And now we run our classifier and we should get some output here. And you can see we get a pretty decent classification. Just with 3 samples of each class, we are able to now generate a map that looks pretty decent. We have mangroves, other and water. And again, this won't be perfect with just a few samples. The way you fix it is you say, oh, I found that this is actually not mangrove, but this was classified as mangrove. So you'd go and say, I'm going to put one more sample as other. Rerun your classifier. And if you do this a few times with a handful of samples, you'll end up with a pretty astonishingly accurate map. And the classifiers will soon learn that, oh, these 2 points you dropped, oh, they are closer to now this other cluster than the mangroves cluster. So you can see in the output, you'll see now much cleaner output, and those will get fixed. If you are working with point data, sample regions is preferred because we just extract the pixel value, is also very efficient. If you are working with polygons and you want to calculate the average embedding vector for that particular region, you use reduced regions. In the supplement section, we have a supervised classification approach where we use polygons, and instead of sample regions, we use reduced regions. And again, this is a recommendation. If you use polygons, use the mean embedding for all the pixels as your input features to the classifier. And that works quite well. Typically, if you do a pixel-based classification, you'll not end up with the smooth cluster boundaries or smooth class boundaries. Here you can see it's very smooth. It is kind of traced out the exact boundary of your mangroves. You'll get so many salt, pepper noise in your traditional classification, which you have to clean them up using post-processing. So again, generally you get much smoother output, much higher accuracy than your traditional classification. In all the examples that we have tested, just a drop-in replacement, don't change anything else. Change your input features with embeddings, change your classifier to KNN, you get 5 to 10% jump in accuracy. So again, no brainer. If you're doing this, just try this out. If you have a classification script or a project, just replace your input features with whatever you've done with indices and elevation, slope, all of that. Replace all of that with just embeddings, change your classifier to KNN. You should see a big jump in accuracy and the quality of your output. And again, fixing the mistakes is much easier. Like just adding one counterexample will fix the whole class. So again, iteratively building your training samples like this, you can build a very accurate map much easily. We'll do an exercise where you will pick a region and you will classify mangroves in the region with just a few training samples. Let's try exercise 3C.
So for the exercise here, you need to classify an image for 3 classes, say mangrove, water, and other. So here you see this image being generated for this region. You can just do the same, remove this geometry and go to your region. And first you need to find out if mangrove is there in the region that you are choosing. So we have this mangrove watch layer that you can turn on to see regions which are having mangroves. And here you can draw a geometry. And then you can run this to create image for this region. Once you have this, we want to create 3 layers with these values, say mangroves 1, water 2, and other 3. So create a new layer, say new layer. And this is your geometry layer. You can change this to feature collection and say mangrove. So the it is lowercase, it should exactly match this because it will be using, you will be using this name in the code below.
It's mangroves.
Okay. And here we are having properties. This we are assigning 1. You can choose color for the training sample if you want to, and put some points where you see mangroves. So you can zoom in and properly take points in regions which you feel are mangroves. And likewise, create another layer and change the property. Say first, say feature collection, add the property. This is water. And this is say 2. And change the color to identify points and take some points over water. So likewise, just have a few points for other class as well over there. Create a new layer, say other, with the line cover property 3, and take some samples. For taking the samples, you can just use this. This is the point, and you can also use pen tool in case you need to shift it or you need to delete the sample. Likewise, once you take all the samples, you can just uncomment these code. So these lines are just merging the samples and doing all the classification workflow, and it will give you the classified image as well as it is extracting the Mangrove image out of all three classes and will display on the map. So try this, take training samples and then uncomment, and you will see your classified output as well as Mangrove output.
Once you have done this, you can uncomment the line below. There is a shortcut control plus /. So if you select the lines and do control plus /, it'll uncomment all the lines. So once you have all the three layers of mangroves, water, and others with at least one sample in each of those, go and uncomment those lines and you should be able to see the output here. When you are creating those layers, make sure you're adding this land cover property there. So we need a property called land cover with the values 1, 2, and 3 for respective classes. And all the layers that you are adding has to be added as feature collections. So you have to change the names to be the appropriate layer, change it to feature collection, add that as a property, 1, 2, or 3, and then add a point there. So we learned how we can create the supervised classification with embeddings with just a few training samples. What this dataset also enables is to build a land cover classification with legends, which were not possible before or were very, very difficult. So for example, this is a project for doing urban tree cover classification. So this was a project where we wanted to map this landscape with different kind of tree cover. So you can imagine if you want to classify a pixel into large parks or isolated trees or gardens or golf courses, those are kind of things which are very, very hard to do with the traditional remote sensing approaches. Since our satellite embeddings dataset has temporal context, has spatial context, has input from radar and other sensors, you can now just continue with your traditional samples, just pick samples for each of this region and build your classification, and you are able to separate out those quite well. If you're using polygons, for example, for golf courses, there is a lot of variance there. So I want to capture kind of the average embedding of a golf course. So I would draw a polygon around here and then use reduce regions to compute the average embedding vector for that polygon. So if you use polygons, use reduce regions to get the mean vector for the embeddings and then use that as input to classifier. And just with, again, few handful of samples for each class, you're able to build land cover map, which is pretty accurate and can separate different kind of land cover. We have the full script in the supplement folder. If you want to try this out and see how you can use polygons along with embeddings, do check out the script. Let's move on to the last part of the workshop. Most interesting new application that Satellite Embeddings enable is object detection. In remote sensing, kind of the two main areas of work involved is one is classification. Most of the workflows will say, I need to first do a classification. Other set of workflows will say, I want to detect some objects. I want to detect an airplane. I want to detect a car. I want to detect a building. Those approaches were typically in the realm of deep learning. So it was not possible with classical pixel-based remote sensing approaches, and you had to learn deep learning or work with GPUs and do this. With the satellite embeddings dataset, now this problem has become much more approachable, and you are able to map and detect objects of different types quite easily using satellite embeddings. Typically, if you wanted to detect certain type of object, you need to train a custom deep learning model for each type of object. You say, I'm detecting buildings, I'll train a model that can detect buildings. You also need GPUs, which are expensive to use, and you can't use your traditional cloud-based environments or your own machine for doing this thing. Also costs a lot of money because for doing any kind of object detection, you need to purchase high-resolution imagery, which are very expensive. And if you want to do this at a regular cadence, you say, I want to do this for every year and build a database, you have to acquire and procure a lot of expensive high-resolution images. Because for medium resolution imagery, you can't really see the object. Since there are embeddings which has captured that object in both spatial and temporal aspects, they will have a very different values. And by comparing what the embeddings look like for that object, you can go and find other pixels which have the similar objects. The traditional approach will need to train a custom model for each object of interest. Embeddings are generalizable, right? They're not trained for a specific object, but they have captured all the kind of patterns for different objects. So by comparing embeddings, you can find similar objects. You don't need to use deep learning. You don't need GPUs. You can just use a simple vector algebra to find similar vectors, right? So again, very computationally effective. Again, you can do this in code editor. You can do this on your own machine with just simple Python libraries. No need to use GPUs or any other deep learning libraries. And this surprisingly works with medium resolution imagery. So our embeddings at 10-meter resolution are able to detect objects which are even smaller than that, or can't even see that in the image, but they're able to detect those objects. So we can use similarity search with embeddings for object detection. Similarity search is you represent embedding as a vector, and you say, I want to find all other places which have a similar vector. How do you find a similar vector? Well, you can then represent the vector in the n-dimensional space and compute the angle between those. If the angle between those vectors is small, that means they are similar. If the angle between those is different, that means they are different objects. The most popular metric that you use is called cosine similarity. So you just say, give me the cosine of those vectors, two vectors. If the values is similar, then they are similar. If the cosine is different, you have different values. This is similar to spectral angle. In remote sensing, people will be familiar with the concept of spectral angle. This is the same thing. This is a more generic approach that is used in machine learning, which is called cosine similarity. If you do a cosine similarity, the output that you'll get is the cosine of the angle between those two vectors will be between -1 and +1. If the value is 1, that means both the vectors are pointing in the same direction. So they are exactly similar. If the value is 0, then the vectors are orthogonal. There is a 90-degree between those two vectors. And if the value is -1, then the vectors are completely opposite. So if you just do a cosine similarity between those two embedding vectors, and if the value is closer to 1, that means they are similar. The value is closer to -1, they are different. This is the formula for doing cosine similarity. It's vector A multiplied by vector B divided by the magnitude of each of those vectors. Very simple formula. You don't require any fancy matrix multiplication, etc. Just simple linear algebra, take an array of values multiplied by an array of other values and compute the magnitude. For satellite embeddings, this even becomes much more simpler. Remember, I mentioned that the satellite embedding vectors are 1 in magnitude. They are length 1. That means the length of both the vectors are 1. So cosine similarity for satellite embedding vectors is just a dot product. Just multiply those two vectors and you get the cosine similarity. So it's a very, very efficient computation. You can run it at a global scale in real time. That means you would say, I have one point, I want to find all vectors that are similar to this, or compute similarity between this vector and all the vectors. Globally, you can just do this in real time. So it's a very simple computation to compute this. We're going to do an example where we're going to find this particular object. So this is an example of a brick kiln. This is a structure that is used to make clay bricks. And you'll see all over in India, it's a big problem because these brick kilns are responsible for a lot of air pollution and a lot of other human rights issues. They're often unregulated. They pop up in areas where nobody knows. And they're also very temporary. So that means you know the location of one, it'll close down, next month it'll open somewhere else. So from a regulatory perspective, mapping this is of high interest. There's a UNDP project where they use a big machine learning project where they procure high resolution imagery, trained an object detection model to detect this at scale. And they are kind of procuring the images on a regular intervals, detecting those and finding the locations of these brick kilns all across India. What I wanted to show is now, if you just get an embedding vector of one location of a brick kiln, brick kilns are kind of unique, has a unique structure. They are spectrally and spatially very unique. If I find all of the pixels which exhibit the similar patterns and have the same embedding, I would have found all the other brick kilns. So just with a simple similarity search, we are able to go and map all the brick kilns without training a custom model. We'll take this approach where we'll select a region of interest. We'll go and find example of one brick kiln. So you can see this is what it looks like in high-res imagery. This is not low. You can't even see this in low-res imagery because this, it requires you to have the spatial pattern. But again, you can see there's a smokestack and there's this unique pattern around this. I want to go and find all of the pixels which look similar. And I can use this similarity search to go and find that. So let's go into our example and see how we can do this. In the exercise, you can pick another object of your choice. We have an exercise for detecting solar farms. So if you go in some solar panels, go and drop a point, you'll find all of the solar panels. So let's see how the similarity search works. We'll dive into code and then we'll come back to the presentation. Let's start on script 4a, where we'll use similarity search to map the brick-kiln locations in a district in India. We start with the GAL 2024 collection. This is a newer district data set that was released recently. So admin 2 regions for the whole world. It's in the community catalog. We apply a filter and select the district of interest. And we then have to add some reference locations. You can even use one location because similarity search will just say compare one vector to all the vector and compute the cosine similarity. Just to have it more robust, you can show a few more examples. So here we have added this feature collection I'm calling samples. We don't need any properties, just a feature collection. So we can hold more than 1 points here. And again, you can zoom in and look at the region here. I'm going to show you the region. So you can see in the high resolution imagery, I have gone and found locations of some brick kilns. A word of note is when you're doing this, you're using the Google Maps high resolution imagery. This imagery's date is unknown. We don't know what date this image was taken. And that means this image might be older. And when you actually get an output detection and you are using 2024 embeddings, you might say, oh, this was wrong because there's nothing here. It may be that there is a newer high-res imagery where you will be able to see it, but the base map is not updated. And similarly, if you're trying to do something for 2017, the image might be newer. So just note that there might be discrepancies in the dates of the images. But again, as a free source of high-resolution imagery, we have this layer available. So we just use it as a reference to drop some points. We said this is one of the brick kilns that we found. Go and show some examples if there are different kinds. In this state, the construction of brick kilns looks like this. But if you go up north in India, they look slightly different. So again, if you want to map those, maybe do 2 different object detections. So again, we found a few examples. And now we say, go and find all the brick kilns in this district. And we want to do the similarity search approach for doing this. First thing we do is we choose the scale. We are using 20 meters here because again, 20 meter, we are able to capture all the spatial context that are in this pixel. So we're using 20 meter scale. And now we have our embeddings. So we say for our embeddings layer, we are using the year 2024. Extract the embedding vector for each of those points. So we have 3 samples, and these are the embedding vectors at these locations. And what I want to do is I want to now say, take this 64-dimensional vector. For every pixel in my embeddings image, I want to compare the cosine similarity between this vector of my reference location with every other pixel. Here's the function for calculating similarity. We take our embeddings image and we use some array math to just do a basic dot product. So here is our every pixel in our embeddings image. And we take our input embedding and we say, for each of this vector, compute the similarity between this vector against this image. And we do it 3 times for each of those points. So now we get this 3 distances. So we have 3 samples. And we now, for every pixel, we say this pixel has a cosine similarity of A with this first sample, B with a second sample, C with the third sample. And we say, just give me the average similarity. If it was, say, 0.9, 0.95, and 1, it will give you 0.95 similarity. Okay, so we just get the mean values. You can also do it the other way where you can say, I will take this 3, compute the average value of this, and then compare it with all the images. So again, you can do average first and then compare it, or we compared everything and take the average of that. So now we have this mean distance, and let's visualize this. So we can say, now for every image, every pixel in the image, we have computed the similarity between the input reference location and all of the pixels. So now if I zoom into a region, you'll see this image where the pixel values are the cosine similarity. If I inspect a pixel, it'll say this pixel has a similarity of 0.91 with this reference location. If I inspect somewhere in the river here, it says the similarity is 0.44. It's very different than the reference location. And this scales beautifully. Like you can do this at global scale. I can just remove this clip and now I can find similarity all across the world in real time because it's just a dot product. So now we can say, show me the similarity to this reference location all across the globe, and it'll just compute that very fast. So now we have found kind of similar locations everywhere in the world. So if you now are thinking about, say, I want to find this location in this region, you can just do this very easily. How do I actually find the locations of other brick kilns? I don't want similarity. This is just a starting point. How do I actually go and find all other ones? We need to decide on a threshold, and we say, select all the pixels where similarity is very close to the reference location. Here we are using the threshold of 0.97. So I say, go and find all pixels where the similarity is more than 0.97. So very, very similar to the reference location. And this will give you a binary image where it's 0 and 1. 1 is all the pixels where you have the location where it is matched. At this point, you can just export this image and you'll get a binary image with ones and zeros, and ones are the brick kilns. It's very, very fast, very simple. For visualizing this, if I just visualize this, there'll be only a few pixels with the matches, so it's hard to visualize. So for visualization, we can actually vectorize it. So we'll go and vectorize it into polygons. So we'll say, take the matches and convert it to polygons. So all the pixels which were detected as brick kilns, convert to polygons, and then just compute the centroid. This is to ease the visualization. And this is the part that actually takes a lot of time. It's a memory intensive operation, converting raster to vector. If you're doing this at scale, I recommend you just take this similar pixels image, export this, and vectorize it in your GIS. That'll just scale much nicely, rather than doing this in Earth Engine. If you're doing this in Earth Engine and you are working in a large region, please export this collection. This is a feature collection. Please export this as an asset before visualizing this, because this is the part that takes a lot of computation to convert it. This part is the simpler part. And now when we have this matches, let's just visualize this. So we now have this predicted matches. Since it's a small region, we should be able to interactively visualize the results. So we are now finding all pixels which are embedding vectors very similar to the reference location. We have converted to vector. And if I zoom in, you can see I found all of the brick kilns. Right. And it won't be perfect, but not bad for 5 minutes worth of effort. I'm able to now find locations which are potentially brick kilns, and you can see I've located all of this, which you may not even realize that there is a brick kiln here. And if you look at the embeddings image, so the resolution of your input data is not good enough to even detect this using any of your deep learning tasks. You can see the pixels are quite big. But since the pixels have encoded all the spatial pattern and the sensors data, you are now able to use this pixel similarity to say, hey, just give me pixels that look similar. And that can be in turn used for object detections. I would see this being very useful where this model may not be very accurate. It'll have a lot of false positive. It may not scale well, but you can use this as a starting point to extract and find locations where there can be potential brick kilns. And then you can say, now I'll use this to extract image chips and train an object detection model. Because even generating the training data is a big task. Here you can now say, I will automatically generate label data for training my custom object detection model. I may have missed some coverage. So even if you want to compare some data set and say, I have some output, can I compare this result? Did my data set miss any brick kilns? Well, you can do the similarity search and say, hey, this was a thing I found here, which my model missed. So again, it can be used in conjunction with your GeoAI approaches, or it can be used as a starting point for a project where you can get something pretty close to high accuracy output, but then you can use some rules to filter out duplicates and other things. What other things can do? Well, a few years back, somebody asked, can I map grain silos? Grain silos are the structures that are there in the US where you're in the farmland, you store the grains here. And again, at that time, I didn't have a good answer because, again, you need an object detection model. Well, when I first saw the embeddings, that was the first thing I tried. I dropped a point at a grain silo, and lo and behold, I found all the grain silos in the entire county. The tutorial I developed for the user guide goes through the process of finding the grain silos. So if you want to try this out, it's similar approach. What else can we do? Well, let's try this out. I think the magic is when you try this and see if it works for your region. Let's try an exercise 4C where we'll try a similarity search to map solar farms. So Vigna, you can explain the exercise.
So here we have the solar farms database. You can use that to to see to choose the region of interest. So here you can just go to some region which are familiar to you and use that for this exercise. So first you will just delete this geometry and create a new geometry at your chosen location. Yeah, so let me just use this one. Yeah, here using this, first we'll just run the code and see how the image looks. And this is your image. And here are your solar farms. You can use this to inspect and get the thresholds for this particular region. So zoom in properly and then try and inspect. Yeah, so let me say what are the values for similarity, and we can use this for thresholding. You can decide the scale based on what kind of farms that you are getting over there. So try this. You can change the threshold and the scale and try this for your region.
The idea is we want to map solar farms. We have a reference layer that was product of a project that was a deep learning project. Somebody built a CNN model that to classify solar farms. We have that polygons. It's not comprehensive. It has got mapped everything, but there are new solar farms that have popped up since. So we can use this as a reference to say, I will select a region. I want to drop 1 or 2 points at a solar farm. Where are those? If you don't want to manually look for those, use this layer as a reference, and then just drop a reference point there, change the similarity, change the scale if you want to, and then run the code to find all of the solar farms. And there's a note here that don't do this in urban areas. In urban areas, the rooftop solar versus solar farms, they are kind of very similar. Similar research won't work very well in this case. So pick a rural region where it's kind of the solar farms are much more unique than other landscape, and you can use similar research there. Let's try the exercise 4C, where we are trying to map solar farms. We have the example here. In this example, we are picking a region in west of India, a lot of solar farms here. We took 2 reference locations, ran through our similarity search, and then we found all other candidate solar farms that were found using this similarity search. And you can see there are a lot of farms which were very hard to spot even visually, but with this, you can just go and find similar pixels here. So go and play around with the scale, play around with the threshold, and see what works best for your region. Let's wrap up. So we've worked through our examples. We finished the similarity search. I want to point you to some more resources that you can use. As I mentioned, there are 5 tutorials that I wrote for the official user guide. We covered some of the approaches, the stuff that we didn't cover. One is the regression. So here is an example of predicting above ground biomass. So instead of predicting a land cover class, we are predicting a numeric value. And here's an example where we can use some of the covariates that usually comes from satellite data. We can replace the covariates in our regression model with the satellite embeddings, use the render forest in a regression mode, and predict the quantity. So you can use the regression workflow from here. If you want to look at the similarity search example that has the grain silos, you can also use this one. There are some references that I've linked to in the slides. The first is the paper for the Alpha Earth Foundations model, just the model architecture, how they tested it, how they validated it. So it's a good read if you're kind of trying to use the data and understand how the model was created. There is a recent preprint that came out where what they found was they take some really high quality training samples from one part of the world, train a model, and then apply the model to a different part of the world, which was a strict no-no before you had embeddings, because then there's so much of variability in the different sensors that you can't really transfer your learnings from one region to the other. And what they found was, I think they took data from the US for different forest types, trained a model, and then applied it on Canada. And they found the accuracy to be much higher than all the existing approaches. So again, what they found was this embeddings can also be scaled spatial into different spatial regions. And again, all of this has to be peer reviewed and they might get changed. So again, watch out for the final versions of these papers. But again, good read if you want to know what people are doing it. I've also linked to some of the other things. This is the paper on crop type mapping without field labels, which is using the unsupervised approach. It's using the Sentinel-2 time series modeling techniques. Same approach that we learned, but we use embeddings. They use kind of a more traditional harmonic modeling techniques. And this is the water detect. We're using the same unsupervised technique for labeling water clusters using the NDWI that we talked about. So again, if you want to read more, you can read those references from here.